Hi everyone, my name is Minxu. Today I will talk about our work of social noise mitigation in focused ion beam microscopy by time resolve measurement, which was recently published in Ultramicroscopy journal in January. What's the structure of the microscopy? Random number of ions coming from the ion source and hit the sample. The randomness of incident ions are the social noise seen in the title. We are trying to mitigate the randomness of ion arrivals. For each incident ion, random number of secondary electrons are generated, then detected by SE detector. There are some limitations of the microscopy. Because the ions are very heavy, it will cause damage to the sample, especially at long scan time. As time increases, we can see that some small features in the red and blue boxes disappear. Our goal here is to make the most of any fixed ion dose. Doing so will equivalently allow us to reduce ion dose for any desired image quality. Now let's shift to how we view focused ion beam microscopy. The yellow arrows represent the incident ions, and for there to be a burst of SEs per incident ion, which are the blue arrows. There is some fixed dwell time, meaning fixed ion dose. In that dwell time, we have a Poisson distributed number of ions m with mean lambda being the dose. We model the number of secondary electrons per ion, also Poisson distributed with mean eta, where eta is the expected number of emitted SE per ion. This gives us a model for the total number of SEs, which we call Y, and our goal here is to compute an estimate of eta for each pixel. We can write the probability mass function for Y at 1 pixel with dose lambda, which we call it Neyman type A distribution. Since the expected value of Y is proportional to eta, as we rest scan, any scaling of Y gives a reasonable image of the variation of eta. This reveals a way of performing conventional estimation, which is the total detected SE divided by total dose lambda. However, we can do better through time-resolved measurements. What we mean by time-resolved measurements is to divide our total dwell time into several sub-acquisitions. When the sub-acquisitions are short enough, we can say roughly that the number of incident ions is the number of sub-acquisitions with at least one SE. This is based on assuming at most one ion per sub-acquisition and at least one SE per incident ion. It gives us an estimator eta QM. Our two other time-resolved methods, called LQM and TRML respectively, use a more precise model. More importantly, we account for the probability of an incident ion resulting in zero detected secondary electron. Shown here is a synthetic visual example. We use the synthetic image on the left, scaled to represent eta ranging from 2 to 8 to generate data pseudo-randomly. Then we compare conventional and 3 time-resolved reconstructions. The improvement is visually and quantitatively apparent. The TRML method achieves an MSE reduction by a factor of 2.6 compared to the conventional one. Two other time-resolved methods achieve substantial but lesser improvements. These results do not use spatial regularization. Our methods are validated with real experimental data as well. Reconstructions by conventional method are shown in the top row of columns 2 and 3. The time-resolved reconstructions for the corresponding doses are displayed in the bottom row. With increasing ion dose, the image quality improves as expected, and our method achieves lower mean square error compared with conventional method. We also compare the pixel-by-pixel absolute error of both methods for the zooming areas shown in the red boxes. We still observe the improvement by applying time-resolved measurements. We've also plotted the root mean square error as a function of total dose lambda for real experimental data. Note that by applying time-resolved measurements, we tremendously reduce source dose by a factor of 5 for a fixed root mean square error. For more details, please refer to our ultramicroscopy paper. Thank you for your attention.